Hello everyone, welcome you all to the technical talk on earthquake resistant buildings. Myself Chandana, Assistant Professor of Department of Civil Engineering, Vedavyasa Institute of Technology. A building may be subjected to various dynamic loads such as wind and seismic loads. In earthquake design, we consider buildings which are subject to random motion of ground at its base. As you can see in this picture, the ground motion is actually acting at the base. So this ground motion induces an inertia forces in the building that in turn causes stress in the building. So the motion of the ground during the earthquake is cyclic about the neutral position of the structure. That is, the stress in the building due to seismic load undergoes many complete reversals, and that too over the small duration of an earthquake. So the engineers do not attempt to make the earthquake engineers do not attempt to make earthquake-proof buildings that will not get damaged even during the rare but strong earthquake. Such buildings will be too robust and also will be too expensive. So instead, the engineering intention is to make the building earthquake resistant. Such buildings resist the effect of ground shaking, although they may get damaged severely but would not collapse during a strong earthquake. Thus, the safety of people and contents is assured in earthquake resistant buildings. Thereby, a disaster is avoided. So, this is a major objective of seismic design codes throughout the world. The traditional earthquake resistant design philosophy requires that the normal building should be behaving as described here. That is, first, under minor shaking, which is frequent, the main members like beams and columns should not be damaged. However, building parts that do not carry the load, such as partition walls, may sustain repairable damage. Then the second philosophy is that under moderate shaking, which are occasional, the main members may sustain repairable damage, while the other parts of the building may be damaged such that they may even have to be replaced after the earthquake. And the third philosophy is that under strong earthquake, that is, which is very rare, the main members may sustain severe, that is even irreparable damage, but the building should not collapse. So these are the three design philosophy for an earthquake resistant structure. So from all these philosophy, we can correlate that after minor shaking, the building may be fully operational within a short time, and the repair cost will also be very small. And after moderate shaking, the building will be operational once the repair and strengthening of the damaged main members are completed. But after a strong earthquake, the building may become will be not functional for further use, but it will stand so that people can be evacuated and the property can be recovered. Thus, a seismic design balances reduced cost and acceptable damage to make the project viable. This careful balance is arrived based on extensive research and detailed post-earthquake damage assessment studies. For this reason, design against earthquake effects is called the earthquake-resistant design, and it is not earthquake-proof design. So now let's look into the principles of earthquake-resistant design of RC members. So the collapse of RC buildings as reinforced concrete building is generally preventable if the following principles of earthquake-resistant designs are observed. That is, first one, the failure should be ductile rather than brittle. Next one, these are some 4 simple principles. Second one is the flexural failure should precede shear failure. Third one is that beam should fail before columns. And the last one, connection should be stronger than the members that fit into them. So as per the first principle, the ductility of a member can be increased with an increase in the compression steel content, concrete compressive strength, and ultimate concrete strength. So as shown in the picture, there should be a ductile performance rather than brittle. If it is brittle, the concrete, the structure may tend to collapse. Now, for the second principle, in order to prevent shear failure occurring before flexural failure, the design should be such that the flexural reinforcement in the member yields while the shear reinforcement is at a stress which is less than the yield value. Then for the third principle, we must always ensure that it follows a weak beam and strong column design concept. As you can see in the left side of the picture, the concept of weak beam and strong column is followed rather than weak column and strong beam. Even that is so, the structure won't be safe. Then the fourth one, we should always note that the proper joint should be made at discontinuities. This is to avoid mounting of adjoining parts of the building. So, for a building to perform satisfactorily during earthquakes, it should meet all the philosophy of earthquake resistant design which we discussed previously. Now, there are four aspects of building or four virtues for earthquake resistant design that the architects and the design engineers work. This is to create, these are actually mainly the four virtues are mainly seismic structural configuration, lateral stiffness, lateral strength, ductility. So these four virtues are actually in addition to the other aspects like aesthetics, functionality, comfort of building. So now let's look into each of these virtues separately. So seismic structural configuration, it is actually including three main concepts. First concept, that's the geometry or the shape and size of the building. Second aspect is location and size of the structural elements. And third is the location and size of the significant non-structural elements. So the seismic structural configuration can be explained using the convex and concave theory. So convex shaped buildings, as shown in the left side this picture, in the convex shaped building we have direct load paths for transferring earthquake shaking, and if it is concave buildings, it necessitates a bending of the load paths for shaking of the ground along certain direction. So this results in the stress concentration at all points where the load paths bend. You can see here over there is a bend in the load path, and this can cause a stress. But in convex there is a direct path. So that is like if you go more into an original picture, that is as seen in the picture, buildings with rectangular plans as shown in this top one, or with rectangular plans and straight elevation, it stands the best chance of doing well during an earthquake because inertia forces are transferred without a bend. This is due to the geometry of the building. But as you can see in the bottom two pictures, that is, there is buildings with setbacks and central openings. It follows there's a constraint in the flow of inertia force. That is, the inertia force parts have to, here it has to bend, here also it has to bend in order to reach the ground. As you can see, it is clear in these two pictures. So that is about the first seismic configuration. So then the next three virtues are the lateral stiffness, lateral strength, and ductility. So what is lateral strength? Strength is actually, it refers to the maximum resistance that the building offers during its entire history of resistance to deformation. And ductility, it is the lateral deformation, or the lateral ductility, it is the ratio of maximum deformation and the idealized yield deformation. And the lateral stiffness, it is the initial stiffness of the building even though The stiffness of the building reduces with increasing damage. So desirable stiffness means the initial stiffness. So so that is the four virtues, the four desirable virtues in the first one. It is the good seismic configuration, that is with no choice of architectural form of the building that is detrimental to good earthquake performance and that does not introduce newer complexities in the building. And the second is at least a minimum lateral stiffness in each of its planned direction so that there is no discomfort to occupant of the building and there is no damage to contents in the building. The third virtue is at least a minimum lateral strength in each of its planned direction, that is to resist the low intensity ground shaking with no damage and not too strong to keep the cost of construction in check. And the fourth one is a good overall ductility in order to accommodate the imposed lateral deformation between the base and the roof of the building. So these are the four virtues. And so how can we achieve these virtues? So the four virtues are achieved by inputs provided at all the stages of development of building, namely planning, design, construction and maintenance. So nowadays we have municipal authorities which arrange to examine if all the required technical inputs have been met to ensure safety of the building before allowing the building to be built, the construction to be continued at different stages or the users to occupy the building. So the different stages are conceptual design stage, design development stage through peer review of the structural design, construction stage. And so through all these, in all these stages, we have to check with the structural resistance towards the earthquake, seismic loads, and also so everything in the construction stage also we have to check through the quality and quality assurance. So that was a brief knowledge about earthquake resistant buildings. In India we follow Indian standard IS 1893-2016 for criteria for earthquake resistant design of structures. Thank you.